Mathematics. That's frustrating. All right. There we go. How's it going, guys? Morning, Nick. Cool. Today's a very exciting day. We have a new Hearthstone expansion coming out this afternoon. I imagine you guys will all be playing. Unfortunately, we'll probably not be able to play until tonight, but, you know, still exciting. We just started cosets and stuff in abstract algebra. If that brings back, you know, fond memories. You know, Nick, you can easily just download the game, and it's actually free to play. You know, it's pay to win, but we ignore that part. It's free to play. Easy. It's even on mobile. Requires way more of your data storage than you would expect for a card game. But that's Hearthstone for you. All right. Pogs indeed. All right. Waiting on a couple more people. Thought that was a quality meme last night from Rippy. It amused me. Okay. Yes, I too feel like we are missing some people. Especially since I still only see like 2 in Twitch. Okay, there we go. Now we've got humans. Okay. Well, I'll get started, I guess. We're missing just a couple. Okay. So I want to make a comment. Looking at the reflections and stuff, at least for those who responded, it seems like Twitch for now seems fine. Zoom would probably also be fine, but it didn't seem like anyone was like strongly desiring to switch things. I did want to make a comment though about just like working in general and how the problem set being due on Saturday needs to work going forward. So just because it's due Saturday does not mean you get to start a whole day late. Well, I mean, I guess maybe it does, but you should not necessarily start a whole day later and expect me to answer as many questions as I was Friday night and Saturday afternoon. That's not really how I envision most of my weekends. So, I mean, yes, I give you extra time, but that doesn't mean you should necessarily push it back and then take advantage of my inability to say no. What I would like, so one thing I'm going to try to do is maybe scaffold a little bit more on the problem set. So one problem in particular that I foresee being on the next one is exercise 208. Basically, this function. So, I think we've mentioned before, or at least the interval from 0 to 1 as being, having uncountably many things and actually being homeomorphic to R. Well, this guy is homeomorphic to R as well. Any open interval of finite length is. And the map I give you there looks like this. That's a very challenging problem. It's not one I plan on doing in class, but this is one that I think scaffolding is very useful. Essentially, like, how do you find the inverse? You use the quadratic formula, and then it's going to be piecewise, and like one piece, it's obvious that it's continuous just from like what you know about calculus, and right, like our continuity from calculus works because we showed that the epsilon delta definition is the same as this open set definition, and then the last part is that you have to show that the other piecewise part, that it actually like goes to what you want it to. So I'm going to try to do that, but I also would like you guys to work together more. Again, this is something I think I mentioned very early in class, and I know that you guys had different schedules and are all insanely busy while you were here, but now that you're not here and you don't have sports practices, you don't have house stuff, or at least not that same kind of house, I would really like you to use Discord more. I don't think I've ever really seen people in the Working Together voice channel doing stuff together on these problem sets. I know that there, just from talking to you guys, there's been like a little communication, but it seems like overall pretty little collaboration on these problem sets, and I think that's part of the reason that I was getting so many questions on Friday and Saturday, is that you're mostly trying to go at it alone. And I think one of the benefits of having a small class, right, is that you can work together. You guys know each other well, and I think that will make things easier. So I highly recommend trying to use Discord to your advantage. Not saying you can't ask me questions, obviously, but I think it's useful to try, obviously, like, attack it on your own first, get the thoughts swirling, but then talk with other people about it. You might find some different perspectives, or they might find a hole in the argument where you thought it was airtight, and then come to me afterward, and yeah, ideally Thursday more instead of Friday night, Saturday. Okay, I have like 3 times as much homework now. That's interesting. Well, I guess you have more time to do it, but yeah, that is interesting. I have tried to keep everything actually roughly the same-ish, probably a little bit less in some cases, but I don't know. Either way, I feel like time flexibility, whether you're working or not, if you are spending time on the topology, then hopefully you're more flexible in terms of being able to talk to other people. All my work is homework because I'm all right. I hate this class. Okay, so just kidding. I love you guys, and I miss you very much. So homeomorphisms. I guess we're not quite there in terms of, we started with 195, but this is important stuff. So essentially, 196 is very similar, and if you remember, I talked about how the discrete topology, you can think of that as having this like universal property, whatever that exactly means, that it is the unique topology that makes every map out of it continuous. So this is a similar way to describe like the subspace and quotient topologies. The subspace is the coarsest topology such that the inclusion map is continuous, and the quotient map or the quotient topology is the finest topology such that the quotient map is continuous. And so these are just other ways to characterize these things. And again, if you like go on in math a little bit down the road, these are very, very useful notions. So 196 will probably just be on the problem set. It's very similar to 195. So let's start with 195 here. So first, if the subspace topology is going to be the coarsest such that this map is continuous, well, it better at least have the map be continuous, right? So we've got our inclusion from, we called it y to x, right? So it's just the identity map, but it's restricted to only things in y, is continuous. And here we are giving y, so unless otherwise stated, it just has its standard topology, which would be the subspace topology. Okay, so I'm just going to run through this part real fast, and then I'm curious to see how you guys approach the coarsest topology thing. So you just look at your preimage of an open set, right? So I guess I'll define that first. So let U be open in X. Well, then so I saw some you used cases or something, but what is the preimage of U in general, right? So U belongs to X as a whole. So we've got Y here, and then maybe my U looks something like this. So what is the preimage of the inclusion map, or of U under the inclusion? Yeah, it's the intersection of U with Y, right? And basically this follows immediately from the fact that I inverse of X is the empty set if X is not in Y. And so once you know that, well, U intersect Y is exactly of the form open intersect Y, so this is exactly an open set in the subspace topology. And we'll say Ty. Okay. All right, so that's nice. Why is this the coarsest? So, right, we're assuming here we said T is some other topology. I guess it doesn't really have to be other, just some topology on Y such that I is continuous. And then what do we want to show here? Because I think, again, starting with what you want to show helps guide your proof. Because I saw a lot of the right ideas, but maybe a few things were out of order logically. So I think it's almost the other way around. Yeah, so what Devin just wrote. So basically, right, to be coarser means that Ty is a subset of T, right? This would mean that T is finer. And so you want to start, in fact, so you don't want to look at preimages yet. That's kind of the thing that you can use. That's part of your assumption that I is continuous for T. But you want to start with some open, say V in Ty. And then this is the subspace topology, so you know what this looks like. Right? V is U intersect Y for some open U in X. Because this is the subspace topology. Okay. Now is our time to use continuity. right? So our goal is to show that V actually lies in the topology T, but we kind of notice, right, this is exactly I inverse of U, and so that's how we bridge the gap here, right? So note that V is equal to I inverse of U, and I inverse of U is in T, since I is continuous. Thus, V is an element of T, and so we get our inclusion as desired. Does that make sense? All right. Well, we will proceed as if things were said. All right, thank you, Jack. It means a lot to me. All right. So, the next one, and there are a couple ways to do this one, but this is another important map, right? So, like, projections are very important. These coordinate functions are very important, right? So you have, like, maps from a product to something smaller, or, like, either to one piece of the product, one factor of the product, or, you know, if you have, like, an n-fold product, you can go to, like, an n minus k-fold product with some projection. We have coordinate functions that help us go the other way, right? We can go upward to a product of more spaces. We have an inclusion. Now we want another idea of just, you know, maybe it's not the inclusion map, but we're only considering the map on a subset of, or a subspace of our space. So this is a restriction map. So basically you start with some f from x to y, and then you just look at what f does on elements of A, and then forget about the things in x that are not in A. So there are a couple routes here. What did you guys do? I'm curious. I mean, I kind of know already, but I'm curious for you to tell other people what you did. Okay, so that's the fast way. And then the other way would be pre-images, right? So we basically have two ways. So method one would be, okay, we know how to show continuity, it's pre-images, right? So like you start with U open in Y, and you realize that what is F restriction inverse of U? Yeah, we'll talk about composed maps in a second. I have to say what maps, I guess. So in this case, like, what would your pre-image of an open set look like? It's somewhat like the inclusion. So it's not Y, right? It's got to be inside X. Yeah, U intersect. So it's the pre-image of U intersect A. Again, because U lies inside Y. But basically, you know, you go back, you have the stuff in X that maps to U, the stuff outside of A you don't care about, because you forget that when you restrict, and so you only care about the things in the pre-image that also belong to A. And again, using subspace topology, this is open. So the other way is to indeed compose maps. So what is the restriction? We said it's like forget the stuff around A, or like not in A, but what are you really doing? A is a subset of X. So what you're really doing is first just saying like, okay, I'm just going to include this inside x, right? So I look at I from a to x, and then I do f from x to y. And so I get f composed I from a to y. And this is exactly the restriction map. Right, because you're still doing f on all the elements of A, but you are only doing it on the elements of A. And we showed, I don't remember exactly what exercise it was, but composition of continuous is continuous. And you just showed the inclusion map's continuous, and f was given to be continuous. So this is continuous. And this can be a useful notion a lot of the time. So like composing things with the inclusion or composing things with the projection are very common things that show up in topology. Questions on that second part at all? Did I have to use the identity map? That seems very pedantic. You mean, like, could I have just said F? It's not pedantic because you have to have it come from A and not X, right? So you have to have some way of starting it in A. Do you have voice chat or no? Every A in A is in X since it's a subset. Okay. But yeah, right. Yeah, it's about the pre-images of opens from the image, and either way, like we need the map, right? Like if we want to talk about F restricted to A, it needs to be a map from A to Y. And so if you just use F and like don't compose with this identity or with the inclusion, then it's not from A to Y, and so you're not going back. Okay. So the next ones were just kind of our typical getting used to things. Hashtag, it's the hashtag never going back. Whatever. All right. So we usually start with these, take a few elements, see what happens, never use it again. But that's actually not going to be the case this time because here we have like the very important Sierpinski topology, right? So Sierpinski space, the particular point topology, is super important. You've already used it for a counterexample, maybe once or twice. It'll show up again. So this one's actually useful. So how many possible topologies are there here? Potentially homeomorphic. So just straight up, how many? Blank. Yeah, so we've got 4 topologies. Right, so we have the discrete, we have the indiscrete, and then you have your 2 particular points, right? So you've got boom, 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 and same thing but with 1. So we're going to be pedantic here, and I apologize, but I think it's useful, at least the very first time you see it, to really think about, like, okay, why are these homeomorphic? Or if you claim that they are not, why are they not homeomorphic? And like rigorously show it, understand how such things are shown, and then, unless it's a difficult space where that's like something you really have to prove, never do it again. That's the dream. So, with this one, I mean, okay. Correct. Topology's in. Yeah. I mean, there's still bijections, so yes. Yeah. Yeah, because again, like, correct. So F is a homeomorphism if and only if F is a bijection. And obviously a bijection means it has an inverse. And so F and F inverse are both continuous. Right, and so like the inverse's existence is usually, that's trivial, right? Once you know F is a bijection. F being continuous, it's usually not too hard to find F being continuous. What's often the challenging part is showing that F inverse is also continuous, because it's usually like not hard to think up a continuous map to start, but going back sometimes can be challenging. That 208 is a very simple example, right? Again, if I write this, and again, this was on -1 to 1. You know from calculus, like, okay, -1 and 1 are my asymptotes. Inside there, this is just a rational function where, and rational functions are continuous on their domain. So, like, boom, easy, F is continuous. Its inverse, though, while it exists, is one, hard to actually define. It takes some work. And then showing that it's continuous takes more work. And so that's a very good example of where, like, one of these is very easy, but one of them is not. Okay. So yeah, that's in 208, and like I said, that'll be a scaffolded problem probably on the next problem set. Yeah, so these are just underlying set maps. So here you really only have two, right? Because it's F from X to X, and so you either have F is the identity, or F is your transposition 1, 2, right? Or I guess, 0, 1 here. So F of 0 equals 1 and F of 1 equals 0. Kind of the only thing you can do. Your set of bijections is Z2, isomorphic to Z2. Okay. So which of these are homeomorphic? Let's actually show the homeomorphism first. So obviously, they're all homeomorphic to themselves, but yeah, which different ones are? Correct. Yeah, so this guy. And the ones that are homeomorphic, right, would be the two particular points. And it's via that map. And so, well, clearly a bijection, right? F is a bijection for sure. Okay, why is F continuous? Well, you would look at preimages of open sets, right? And like you don't need to take a ton of time on that, right? The preimage of the empty set is the empty set, the preimage of X is X, and the preimage of 1 is 0, and that's open. So F is continuous, and then F inverse is also continuous, basically the same thing, except for F inverse, the preimage under that of 0, which, again, here, right, preimages for bijections are literally equal to the things you map to, so this is F of 0 or 1. It's a good question. You should at least understand why you're writing F. Yeah, so I mean, I guess yes, you can write F, but like it is, right, you are looking at the pre-images under F inverse, which, like, is F, but yeah, as long as you understand why you're doing what you're doing, then yes, that's fine. I was just, again, maybe being a little pedantic there, but wanted to make clear why this implies continuity. And really, like, after this, right, we have that theorem 203? Yeah, 203, where homeomorphism if and only if f of u, u is open if and only if f of u is open. And there, right, you no longer have to say anything about the preimage of f inverse. You can just use f. Yeah. What do you mean by that? Correct. Yeah, only preimages of open sets. Right. Yeah, because we only take preimages of opens to see if they are open. Okay. And so why are the other ones not homeomorphic? Right, so you can say that they, like, look different. Right. So how would you argue it? That's mostly the right idea, though. Matter of. Okay, so in particular, what I notice here is, like, singleton sets, right? So the discrete has two open singleton sets, whereas the other ones have at most one, right? So I know that F inverse of this is open, and so if this was F, F inverse of 1 is open. If, right, so I'm saying, like, assume F is a homeomorphism, we'll get a contradiction. Now, this is a bijection, so these preimages are also singletons, correct? And F inverse of 0, F inverse of 1 are singleton sets. Well, thus, they must be equal, since no other topology has greater than one open singleton set. But then it's not a bijection. Whoops. Sorry, then F is not 1-to-1. Well, I guess it's not a function, right? Then F is not a function, so this is a contradiction. Because we just had one thing mapping to two different things, which is impossible. Wouldn't matter if a non-opened mapped to an open. Oh, is that going back a little bit? Sorry. It wouldn't matter if a non-open map to an open. It would matter if a non-open map to an open. That would mean it's not a continuous map, right? So that would mean the pre-image of an open set would be not open. So your map would not be continuous in that case. Does this make sense? So basically, right, like what I'm looking at here is I've got 0 and 1, and essentially I know both of these go back to open, but you know, if I'm looking at like the particular point, this one, this means that the pre-image of 0, 1 is 0. So that f of 0 is simultaneously 0 and 1, which is impossible. And so you get a contradiction. So the danger, and I think, Nick, what you were doing, it was very close. The issue is I think you were kind of assuming the identity map. Right, so like with the discrete, it is finer, but the fact that the pre-image of an open needs to be, like, I think you'd have to just argue a little bit about why that couldn't be a bijection. I think it would be somewhat similar to this. But yeah, the issue there is you don't know that like f inverse of u is literally still u. It's just some open set. And that makes it harder to work with. Okay. So 202, I think you can do something similar. How about you guys toss me... Well, first, toss me two things that are homeomorphic and have 5 elements, either in chat or Discord, wherever, and then we'll come up with a third that's not homeomorphic, because basically you had 2 options, so it's a race to see who gets to choose their T1 and T2. Okay? Seems pretty reasonable. Sure, go for it. Yeah, so the last one's the particular point on B. Okay. Yeah. So in this case, yeah, so T1 is homeomorphic to T2. And again, your map should be obvious, right? It's got to be a bijection. You're really just focusing on the underlying sets, like what elements go to what elements. And so if you had telepathy, you would probably know it because you'd already be reading each other's minds. All right. I feel like that's rarely a might statement, you know? So here, all we have to say is where it sends A, B, and C, right? I think it basically boils down to like 10 options when you think about it, because you know you have to have at least one singleton, because any pairs of any 2 pairs must intersect in one way, and so you know you have to have at least one singleton, you have the empty set, and you have X. So you basically have 5 remaining sets because the power set has 8 elements total, and it's 5 choose 2. So I think you literally have like 10 different things you could do. But that doesn't really matter. So anyway, so if we're going from T1 to T2, well, they both have B, so that seems fine. That should probably just stick with itself. And then the only difference, right, is that this one has A while this one has C. So You just have this map, and then you would check again that you actually get a homeomorphism. Right, so the fact that this is a bijection is clear. And then, do you want to go through the open set argument? I mean, basically, right, like, you can just draw the lines. Like, the pre-image of this is this, this is this, this is this, boom, boom. And then if you do the inverse, you just run the same arrows. Cool. Yeah, you do that. You draw arrows. It's fun. All right. Well, do we need to? Should we? You should know how. And, you know, on a problem set or a test, you would probably have a slightly more challenging thing than this, or you would have theorems to use, right? So knowing certain maps or yeah, a lot of time this is hand waved. Both have to be continuous, so yes, you have to look at pre-images of both. No, otherwise, right, the definition would just be different. Right, because it's already a bijection. If you assume F continuous, like, if that somehow implied F inverse was, then we would not define homeomorphism this way. I'll imagine that we will see an example soon where you do get one way and not the other. Yeah. Okay. So it's maybe more interesting to think of, like, why is T1 not homeomorphic to T3? Can we argue why this is true? Can you use maybe what I did with my strategy up above? Okay. Okay, so you're going from T3 to T1, and you're saying the pre-image of both of these singletons have to be B because this is the only singleton. Yep. Okay, then F inverse of A equals F inverse of B equals B, since B is the only open singleton. In T3. Thus, F is not one-to-one, a contradiction. F inverse of whatever. F is not a function. F inverse is not one-to-one. I can fix this. Why? I have two things mapping to the same thing, so it's not one-to-one. You don't want to read my mind. Minds are terrifying places, or at least, I guess I only really know mine. Okay. This is no comment. No, I don't think it's all obvious. But there are definitely times where I physically become more patient. I steel myself. because I don't think I'm a naturally patient human. I think it's very much become an acquired skill, and so I would hate to always share. Also, like, I'm not always thinking about math. I don't want you to hear other thoughts. Quick, I have to humor them so they don't feel bad. We should probably leave this track because I'm an honest person and I'm terrified at what I might have to say. All right. Do we really need to show that two things map to the same thing, or we can just use that they have different topologies? No, because so different topologies, right? The two that are homeomorphic also have different topologies. They look the same, but that is like the definition of homeomorphism, right? So what you're really saying is like they have different looking topologies, and then you're just a hop, skip, and a jump away from xenophobia. So we've got to show it. Oh, cardinalities. Well, so the cardinalities, do you mean that, like, what do you mean by that? I think it's a similar argument. Like, you're kind of assuming that these things have to map, like, to each other, right? If I'm interpreting you correctly, you're saying that, like, these would match up. Turn this off. Like, these guys would match up, these guys would match up, these guys would match up, or something like this, and therefore, like, these would have a different cardinality, and so that would be bad? Is that what you mean? Number of open sets. No, they have the same number of open sets, right? They all have 5 open sets. Alright. Does that make sense, Will, or I'm not sure I'm full. Oh, sure. Wasn't sure if I was, like, answering a slightly different question than the one you were asking. Okay. I just meant in the case where there's... Oh, if they have an unequal number. So you would still basically have, like, a bijection argument. So the issue there is... so assume you have, like, fewer opens, more opens. Like, literally more, not like this has infinity plus 1 or something, can't do that. Like, literally a greater cardinality. Then if this is 1-to-1, right, then each of these, so then F inverse of U is not equal to F inverse of V if U is not equal to V, since F is a bijection. And so in that case, yeah, you would get too many opens over here, and so you would get a contradiction. You would have to conclude that one of these was open, and it would contradict this assumption. So yes, if they have different numbers, you are correct. You could kind of use this argument. And there, right, to get the contradiction, it's important to go from the one with fewer to the one with more, because you're talking about pre-images and going back. So it's like a pigeonhole principle kind of argument there, right? Okay. Q-will. Okay, so 203, I did actually prove the whole thing back in my home when I had fun times, but I really don't think it's like super illuminating, and we really won't use the last one all that much, so I just feel like it's not necessarily time well spent when we have so much cool stuff to get to. So I just want to do 1 implies 2 implies 3, right? So basically we have F is a homeomorphism, U is open if and only if F of U is open, and similar thing with the closed, right? So C closed if and only if F of C is closed. And this, right, for Nick's question earlier, is where we can really truthfully absolve ourselves of using the F inverse, the inverse image under F inverse, because yes, that is F, but now we've really stated it in a way that we only need to use F. So I'm completely good with you doing that from now on. Sometimes it's actually fun doing these topology things, to be honest. Okay, so this is from X to Y, since we will, use things. So 1 implies 2 should be pretty quick, and then 2 implies 3 and 3 implies 1 are very, very similar. So I think maybe we'll only do 1 unless we feel uncomfortable with it, and then I'm happy to do the other direction. So for 1 implies 2, this one is basically by definition, right? Because we know F and F inverse are continuous, and F of U is equal to the preimage under F inverse of U. And so this just follows immediately, right? So 2 follows immediately from these. Is that clear? That is me being a bit quick, obviously, a little fast and loose, so feel free to say, please show. Yeah, so for all, but that's only one direction, right? That's only one direction. What? Okay, let's see it. So I don't think you need to do that. Here, let's just do it then. So for all U open, I don't think you need that. So this direction is basically what Nick was saying. So if you have an open set in X, then the preimage under F inverse gets you back. So then F inverse of U equals F of U is open in Y by continuity of F inverse. And then, so if F, oh, I understand. Okay, so yes, but I think it still follows pretty much immediately, right? So if F of U is open in Y, then F inverse of F of U, to me that still works as immediately, but maybe your definition of immediately is different than mine. Yeah, so equals U is open in X by continuity of F. Quickly, but a different argument. I mean, it's the same argument pretty much, right? I mean, you're just taking the preimage of the set under that map. It's the same thing. You don't need theorem 30. It's a bijection, right? I don't think you need to state like a theorem for a bijection to go both ways and give you back the same thing. Okay, sure. I don't know. Your mileage may vary. But yeah. Okay. So 2 implies 3. So we want to show stuff about the closed sets. We know stuff about the open sets, right? So we know U open if and only if F of U is open. We want C closed if and only if F of C is closed. So what were the key ingredients here? Pull the complement out and bam, you're done. Yeah, that's pretty much right. So I think what you're really stating there, right, is that 27. Okay, so you're turning it into complement. So you're saying C closed means x minus C, or C complement, is open, and f of x minus C is equal to f of x minus f of C, which is y minus f of C, or f of C complement. So f of C complement, which looks weird because you have like C to the C, so I'll just make it like small weird looking C, is equal to f of C complement. So I think that is basically what Rippey is saying. So I mean, yes, that is the basic idea. That's theorem 27. Oh, but it's a bijection. So it's the preimage of F inverse. Yeah. Yeah, so sorry. F inverse, so use. Sorry. Yeah. I should have made that clear. This is easy. I'm going to cry. Yeah, so that's the fast way here. Using the preimage. And then the other way, right, would be F inverse of the complement of f of C is equal to F inverse of y minus F inverse of f of C is equal to x minus C. Yeah. So that pretty much works. And so, right, use 2 to say the preimage of the complement is open. And so its complement is closed. All right. I don't know what's happening anymore. I'm not happy. All right. 3 implies 1 is very similar. Right, so here you start with open sets, or well, you want open sets, right? So start with an open, its complement is closed. And then you use the same argument. At least it works for non-bijections. Yeah, but then it's not going to be a homeomorphism. Yeah. Okay, so does this make sense? Like what we're doing with the preimages, right? So it's really just like really leveraging 27 over and over again here. Because I can show the details on 2 implies 3 if so desired. If 3 implies 1 if 2 implies 3 didn't make much sense. Well, so I mean, bijection literally means that F composed F inverse is the identity, and the F inverse composed F is the identity. Sorry, that's just wrong the way I wrote it, because it's different identities. The important things. That was terrifying. All right. What do you mean the important thing? No, this is the important thing, right? Like that is exactly what I'm using there. Yeah, but that's because I know that F inverse inverse equals F. Right? So like that. I'd like to see the 3 implied x1 if possible time-wise. Okay. Right. So we start with an open. Choose whichever one you want, right? So if we want to show F is continuous, for instance, then let's start with an open V in Y. Well, then Y minus V is closed. Actually, yeah, whatever. So F inverse of Y minus V, which is equal to F inverse of Y minus F inverse of V, which is X minus F inverse of V, is also closed. So F inverse of V is open. Right, so you're basically just like, you take your open, you make it closed by taking the complement. Well, you don't make it closed, but you get a closed set by taking the complement. You take the preimage splits nicely, you use 27, and then you have the complement of the preimage is closed, and therefore the preimage itself must be open. And then the other direction would be pretty much the same, right? So like U is open in X, then F inverse of X minus U is F of X minus U. This is F of a closed guy, so it's closed, but by 3, by 3, X minus U is closed, and so U is open. And thus, F inverse is also continuous. Okay. So now we're on the Hausdorff one, right? Okay. So the Hausdorff one, I think a lot of you had the right ideas, but again, you weren't necessarily starting in the right place. So, if you want to show Y is Hausdorff, you need to start with points that are not equal inside Y. So a lot of you were saying like, oh, any 2 points in X will have like disjoint open neighborhoods, and you just like map them over to Y, which is like basically the idea, but you're not starting at the right spot, right? So like the order of logic is just like a bit off. So you want to start, so first of all, this is a homeomorphism. So you start with like say Y1 and Y2 that are not equal in Y. So then you want to leverage the fact that X is Hausdorff. How are you going to use that here? How do you start from Y and then utilize the Hausdorff property in X? Yeah, so okay. Right. Yeah. So you're right. Yeah, you could go the long route, but I would also be fine. Again, yeah, it's a bijection, so the right it would have to violate being 1-to-1 in order for these to be to have a non-empty intersection. So I'm fine with you saying disjoint things go to disjoint things because it is indeed 1-to-1. And then yeah, so we have open neighborhoods around our points that are disjoint, and thus Y is Hausdorff. Cool. Okay. So then we can immediately use this in 205. So we have R with the standard is not homeomorphic to R with the finite complement topology. Which makes sense because one is standard and one's super weird. So you would hope that they are not homeomorphic. There are probably other arguments you could use here. But since we've already talked about R with like the countable complement, the same argument shows. So I think that was back somewhere in the 120s, right before the boundary and like end of chapter 1, right? That R with the countable complement topology was not Hausdorff, and this is not Hausdorff for the same reason, right? You have like very infinite sets, uncountable sets that cannot intersect trivially. Okay. Sure. Okay, so you're saying like so you're saying like X is a singleton in RFC, and you want to show that it's not closed. Okay. Right. So enough to show. Yeah, it is. Yeah, so the key here is that that is only a one-way statement in 127. Right, it's not an if and only if. Yeah, that would be an equivalent statement, but here the if isn't satisfied, so it's not a contradiction. Right, because it would be like if the yeah. Correct. Yeah. Yeah, so okay. Yeah, so I think the main thing here would be basically like mimic, I guess, non-Hausdorff argument. Hausdorff argument for RCC. Right, basically you had two things that had to be countable with their complement. In this case, they would be finite, the union to all of R if you had disjoint open sets around this, and that's impossible. You also did this on, I think, your take-home test. Like, I think we did it like once in class, and then it was either on a problem set or the take-home, and then here again. So, yeah, it should be a somewhat familiar argument here. So basically, yeah, RFC is not Hausdorff. I don't remember it, sorry. Oh, I see. I'm not sure if I said anything. So not exactly as you wrote it. So right, if I recall, you said like this guy is a basic open, and so this guy would have to be open by 203 in RFC. But I think you wrote that this would be equal to like the interval from f of a to f of b. So that's not necessarily true. So the issue there, right, is again like f is just a bijection, but it could be really weird. It could space out the points a bunch. It doesn't even need to be an interval. It could end up, you know, spreading all the points inside out, so that you ended up with like a uncountable like discrete set. The key though is that the cardinality, yeah, so it doesn't really work because the cardinality is uncountable. So like AB is actually in bijection with all of R, and so ostensibly you could map this to something that has a finite complement bijectively, which is kind of crazy, but possible. So I'll write down what I just said. So you could theoretically map AB to something with a finite complement. And this is the crazy thing about uncountable things, right? So, yeah, it makes life weird. It's kind of cool, though. Okay. So then we have 206. So this one's pretty quick, right? So the first one was the non-empty open sets. So U not equal to empty. Cardinality of U is, say, in. So it's finite. Then this is a topological property, right? So again, topological property just means that if X has P and X is homeomorphic to Y, then Y has P. Well, even if everything is not necessarily uncountable, everything is just really hard if you can't count. Right, so basically homeomorphic things have the same topological properties. That's just how we define this. So nice. So in this case, right, like f of u has the same cardinality because it's the bijection, right? So this is clear. And you also need really the preimage, right? So like really it's like a V is a subset of Y, then F inverse of V is open, so F inverse of V is finite. If all things are, wow, we are really big braining in there. Okay, so we have an immediate usage of this, right? So 205 just followed immediately from 204, 206.2 just follows immediately from 206.1. So think about the digital line. Well, we know our basic open sets are all finite, right? No, this is true. Just having an open set is the thing. So the first argument was correct. I read that wrong for a second. Okay. So yeah, its basic opens are finite, and then ZFC, well, all its opens, all its non-empty opens, are infinite, right? Because they have to have a finite complement, and they're inside Z, which is not finite. So all finite, none are finite. So by 206.1, not homeomorphic. So that was hopefully fairly straightforward. Just kind of getting you used to using a couple of these topological properties. So right, like Hausdorff is a topological property. Having non-empty open sets that are finite is a topological property. We will see some more topological properties later that are very important. Is there a bijection between finite open sets then, if you defined a map on the topology? Yeah. Yeah, because all finite open sets have to map to finite open sets, and obviously the preimage will do the same thing, and since it's a bijection, there will at least be an open set. Yeah, there will be one. You can pair them off. Yeah. Okay, so the last thing. Oh, never mind. Just kidding. It's 11. Even though you guys came a little late, so 207 is really fast. Basically, it's a very nice property that being homeomorphic is an equivalence relation. So, right, this should be similar. So I'll just like say the idea. So homeomorphism is an equivalence relation. And we basically have all the tools to make this like a 2-minute problem, hopefully. But the reason this is nice, right, is, you know, if you didn't know I was in topology right now, this looks exactly like the statement that isomorphism is an equivalence relation. And we use that a lot in group theory, right, because this allows us to really just talk about equivalence classes under the relation of homeomorphism. And so basically we say spaces are the same up to homeomorphism, the same we said, like, you know, there's only one cyclic group of order n. I mean, really, there are as many out there as you can possibly think up in terms of ways to cycle back. But they're all isomorphic to Zn, right? And that's all we care about. And so this is the same basic idea, that we usually consider spaces up to homeomorphism. So, you know, when you're thinking about like that vertical line, you could just do 3. 1 and 2 makes sense quickly. Okay, yeah, so 3, I mean, G composed F is continuous. Well, first of all, it's bijective, right? Because composition of bijections is a bijection. Composition of continuous is continuous, because we've done that. Continuous is continuous. And then G composed F inverse is equal to F inverse composed G inverse because of socks and shoes. And again, these are both continuous, so again, composition of continuous is continuous. And so, hooray, we get transitivity. Yeah. So now, if it looks like that thing that you know, you can just say it's that thing you know, because we care about things up to homeomorphism. Okay? All right. That's all I've got. So I'll be around for a bit. I have a my research meetings moved to Tuesday, by the way, so it just like worked better for my collaborators. So those are like 1 to 2 on Tuesdays now. So my Thursdays are actually like super free in the afternoon. But I'll be around this afternoon as well, except we have a faculty meeting at like 4:15. But have a delightful day.